Okay, I don't know what I have to do to keep this thing in focus. And this isn't necessarily helping right now. It just doesn't want to be in focus. Okay, there we go. Okay, I'm going to keep that picture up there just to keep it, give it something to focus on for a few minutes. Okay, so again, the transpose of the matrix, the rows of the matrix become the columns. So you see that this column is the same as this row. This column is the same as this row. So if you wanted to look at the columns become the rows, the 1, 2 becomes 1, 2, right? 3, 4 becomes 3, 4, negative 2, 1 becomes negative 2, 1, right? Okay, if I multiply a matrix by its transpose, well, first row times first column, the numbers all match up, so I'm just squaring these numbers. So I get 1 squared, 3 squared, negative 2 squared, I think this is 14. Then I multiply these numbers by these numbers, add them up, I get 12, I think. Okay. Now, we multiply this row by this column. Well, this row matches this, and this column matches this, and I just multiplied this by this to get this, so it's got to give me the same thing. And that's important, because this matrix turns out then to be what we call symmetric. And later on, you'll see that that's a really big deal. Symmetric and anti-symmetric matrices. Okay, well, then I continue on and multiply the second row by the second column. I just square these numbers. I get 4 and 16 and 1, which is 21, if I did that right. Check my arithmetic, okay? There's A times A transpose. This is symmetric. And to be specific, it's symmetric about the main diagonal. Now, just to explain why that is, it's because the row and column you multiply to get this number, the same as the row and column you multiply to get this number, except the column is the row and the row is now the column. Okay, again, this times this gave me this number. This is the same as this, multiplied by this, which is the same as this, gives me the same thing. And you want to sort that out. You want to really understand that. Okay. This becomes very, very important later on, and extremely important if you're trying to do the cosmology of the universe. We'll get to that maybe next week. No, we're not getting there, okay? That's, you know, another really tough abstract algebra and linear algebra course, and then graduate level abstract algebra and linear algebra, and you read a lot of articles, and you work toward your PhD, and then you still don't know anything, but you start trying to get there, okay? So, and you know, not likely to have goals of becoming cosmologists, okay? And I'm 90% sure that not one person in 10,000 has the aptitude. You know, that together. Okay, so we can get this. And it's the good stuff, okay? Again, very important. Okay, so a symmetric matrix, well, that's what it means, right? Okay. And anti-symmetric, this number would be the negative of this number. That would be an anti-symmetric matrix. You can read about that. It's an easy concept to understand. I'm just telling you, you might not know where that goes. You might not know why it's important, but it is. Okay. Now let me just check the things I don't want to forget to talk about. Let's take a matrix and square, just as simple matrix. Okay, so this is another matrix. I'll call it B. And I'm just going to use 1, 2, 3, 4. What's B squared? Well, multiply the matrix by itself. And you get 1, 2, okay. That'll be 7. And multiply here, you're going to get 2 and 8, which is 10. And you're going to get 3 and 12, which is 15. And you're going to get 6 and 16, which is 22, maybe. Again, question mark there. I'm not worried about whether I did the multiplication right, but you get the idea that there's no way you can just look at these numbers. It's not like you square this number, square this number, square this number, and square this number. Okay? This doesn't work unless the matrix is diagonal. Okay, zeros everywhere, put it on the main diagonal. So here's your main diagonal again. To do C squared, this does work. Now I'm not going to do the multiplication, but you really ought to make yourself a note and go ahead. Looks like a 4 and a 9. Just it squares all the numbers in the diagonal. Okay, so that's a kind of important idea. And again, just like symmetric matrices and transposes and all that stuff, you won't know until sometime in April how all this stuff folds together. Right now, we're anticipating that we want to get the idea of a symmetric matrix in your head. We want to get the idea of a diagonal matrix in your head because they have some special properties. Okay? And matrix times its transpose has to be symmetric, and you want to understand why. Then you have some insight into what a matrix is and into some important properties of matrices that you'll appreciate much later. Okay? It's like what I was talking about earlier. You get these things into your brain, even if you kind of forget them in the turmoil of learning everything in between here and there, it's still going to be there. So you're going to understand later what we're doing with these things much better than if you hadn't locked into it at this point. Even if you lose it a little bit, it'll come back to you. But if you don't work with it a little bit right now, it won't, and it's going to be much harder to understand later. Okay, so that's kind of a big deal. Matrix algebra is really simple. It's just like, the rules are just like those for regular algebra, with one exception. And so for matrices, we have a distributive law. Okay, and there's another distributive law with scalars. You'll read about them, you'll understand them. I don't think you're going to have any trouble with it, so I'm trying to focus on things that might be a little harder to understand. Okay, so we got this. Okay, there's associative law for multiplication, associative law, or distributive law. Okay, and of course there's an associative law for addition. If you're doing A plus B plus C, it doesn't matter if you do A plus B first or B plus C first. There's also a commutative law. Okay? Because all you're doing if you have two matrices is you're just adding, you know, if you were, well, I don't have two different matrices. If I wanted to add this matrix to this matrix, I just add the 1 and the 14, the 2 and the 12, the 3 and the 12, the 4 and the 21. And I think you're familiar with that. Okay. Now, one thing you don't have, this looks just like the rules for algebra, right? This is linear algebra. There's an algebra with this thing. The rules are almost the same. Big difference is, and also, well, one other thing. Is the identity matrix. Go plus there. If you multiply a matrix by the identity matrix, you get the matrix you started with. Okay? It's just like identity matrix acts just like 1 does for multiplication. Multiply a number by 1, that's what you get, the number. Okay? In the identity matrix is 1, 0, 0, 1. Multiply a couple of matrices by identity matrices, and you'll understand. Okay? So I recommend that you do that just to convince yourself that this really is true, and to convince yourself of why it's true, because if you don't know why it's true, you lose track of the fact that it is true. Okay. Now, the one exception, you might want to say that A, B equals BA. Okay? Because, of course, that's how numbers work, right? But it doesn't work for matrices. Read the examples. Or make up two matrices of yourself. Take this matrix times this one, and then take this one times this one. Okay? Probably not going to work. This being symmetric, I don't think is going to cause the product to behave the way you would hope. I won't rule it out because I haven't actually proved that in my head right now. Not so. Okay? Now, another big deal is you can have a matrix equation. Equation AB equals C. Okay? And let's say you want to solve for B. Okay, well, we'll write one more property down here. Don't really have room to write it. I'll write it here. A inverse times A equals the identity. Okay? Now, that doesn't work for all matrices. This is true. As long as A can be reduced to I. You know, the whole row reduction thing with matrices that you have done, okay? So you understand how you reduce a matrix, and you understand that some matrices, if you reduce them to I, if you try to reduce them to I, you end up with a row of zeros, you don't get the identity matrix. Because the identity matrix has to have ones on the whole diagonal and zeros everywhere else. Okay? If it has a row of zeros, then there's no one on that diagonal. And it doesn't work as an identity. Also, implicitly, A has to be a square matrix. Right? In order to do its inverse, you have to be able to reduce it to the identity. And the identity has an equal number of rows and columns. So matrix you're reducing has to have an equal number of rows and columns, otherwise you can't reduce it. So the identity, you can reduce it, and that's an important thing to do, but you're not going to get the identity unless A is a square matrix, equal number of rows and columns, okay? So if we have this, for A is a square matrix, B doesn't have to be, C doesn't have to be. Of course, the dimension of B determines, the dimensions of A and B determine the dimension of C, as you I think understand. Yeah, if you don't totally understand that, again, it's a statement that you want to ponder. The reason for it is very simple. Just make up a couple examples and see why. And you need to develop the there's a word for it. It's a buzzword. So naturally, I don't remember it. Okay. But you need to develop the proactiveness to explore things without being told do this, and do this. So a simple example is just make up simple examples of matrices A and B and see how the dimensions of A and B determine the dimension of C. Don't memorize the rule. See why the rule works. And understand proofs to the best of your ability. That's just, that's fairly challenging at this point. And you're not going to get really good at it for a while. Okay. Okay, anyhow, you got a square matrix, A, B equals C. Easy to solve for B. You can't multiply by the reciprocal of A, but you can multiply by the inverse, which is equivalent, right? There's no such thing as a reciprocal of a matrix. So there's another place where matrix algebra doesn't look exactly like algebra for numbers. Okay? So that you get I times B equals A inverse times C. And the identity matrix times any matrix just gives you that any matrix. Okay? I'm going to do an example of that. With just a 2x2 matrix, because it's easy to figure out the inverse of a 2x2 matrix. Okay, so let's just take I'll just use 1, 2, 3, 4. What the heck? Okay. So I want 1, 2, 3, 4 multiplied by the B matrix, which I'll denote x1, x2. And that's got to equal. So now let's think about the dimension. What's the dimension of this matrix have to be? Well, we multiply this row by this column, the result goes in the first row, first column, right? Multiply this by this column, the result goes in the second row, first column. And there's no second column because this thing doesn't have a second column, right? So let's just set this equal to 3, -2. Now, the inverse I should write that down somewhere else. I don't have a good place to write it, so I'm just going to bring that right there a little bit. The inverse of this matrix is this matrix, okay, divided by -4 -6, -2. So that equals -2, 1, 3/2, -1/2. Now, where I get the -2, your book tells you, but I just multiply this diagonal just before. I multiply this diagonal, gives me 6. And I do 4 minus 6. This one minus this one. That's easy. You'll understand it. And you're welcome to do this to convert a 2 by 2 matrix. If I remembered correctly how to do it, because I wouldn't do this. Okay. I will reduce it in my head, sorry. And probably make a mistake. So maybe this is better for me. But let's just check and make sure that this really is the inverse. Let's multiply 2, 1 by 1, 3. I get negative 2 plus 3, which is 1, right? That would be my upper left-hand corner, 1. So that matches the identity matrix. Okay. Then if I multiply this row by the second column, I better get 0, right? Because the identity matrix has 0 there in this first row, second column. So first row, second column gives me 2, and negative 1/2 of 4 is negative 2, gives me 0. So I'm getting optimistic. Okay. I'm not totally sure this is right. So I want to check it. I'm 90% sure, not 99. Because I haven't actually worked it out in my head right now. Okay, then 3 halves, negative 1/2, right? 3 halves times 1 is 3 halves. And negative 1 times 3 is negative 3 halves. That gives me 0. Well, that's second row, first column, and that matches. So I'm getting, I'm 96% confident right now, but let's check the last one. 3 halves times 2 is 3. Negative 1/2 times 4 is negative 2. Negative 4. Getting ridiculous. And that gives us 1. Okay. So if I multiply this by this, I do get the identity. So now I can write this matrix equation. I'm just following what we do here. Okay, so this isn't really part of the solution. But now the solution is we multiply negative 2, 1, 3 halves, negative 1/2 by both sides of the equation. I just barely got room to do this. Okay. Now there's going to be a watermark. I'm actually going to lower the camera just a little. Well, I know multiplying this by this gives me the identity, so I've got 1, 0, 0, 1 times x1, x2, and I'm sorry to be writing so small. Can you tell what I'm writing? You got to get up close and do just try to stab it in front of the camera. And then I just multiply this. Negative 2 times 3 is negative 6. 1 times negative 2 is negative 8. So I get negative 8. And then 3 halves of 3 is 9 halves. Negative 1/2 of negative 2 is 1, which gives me 7 halves. You might not be able to read that. But of course, now 1, 0 times 0, 1, you multiply it out, it just gives you x1, x2, right? So the identity matrix times any matrix compatible with it just repeats that matrix, okay? But again, I've already advised you to multiply identity matrix times a few matrices to get the idea. This tells me that x1 is negative 8, x2 is 7 plus 7 halves. Okay? Make sense? That's how I solve a matrix equation using the inverse matrix. Now, there's a simple rule for inverting a 2 by 2 matrix. Doesn't work for any bigger matrix. For bigger matrix, you have to do something different. write the augmented matrix A, I, and you reduce that until A is reduced down to the identity. And of course, whatever you do to a row, you do to the whole row, including the matrix, what you have in the identity matrix. And when you're done, you have the inverse. So let's go ahead. I'm going to ask you to actually put this out. Okay. Let's see how you do. At least we'll let you get started. We don't want to spend too much time on it. We've got 30 minutes left. Just out a number of things. Okay. So let's try. Okay, the augmented matrix AI for the matrix 1, 2, 3, 4. Here's your A matrix. Here's your identity matrix. Okay. Well, reduce that down to Gaussian Jordan form. Okay, completely reduce the matrix. You will end up with the identity here, and you'll end up with the inverse here. So go ahead and do that. Okay, well, the row reduction. You're just gonna make sure we've got it and have an example. Okay, you're gonna do row 2 minus three times row 1. Okay. I hesitate to say it, but I say it's better than, well, never mind. Okay, anyway, we've got 1, 2, 0, 1. And that's going to give us a 0 here. Subtract 3 times 2 from 4, we get -2. And subtract 3 times 1 from 0, we get -3, 1. And then we take -1/2 of the second row. And we have 1, 2, 0, 1, 0, 1, 3/2, 1/2. 3/2 -1/2. You notice that already matches the second row that we know works. Okay. But we still don't have the first row because we haven't completed the reduction. We've got to subtract double the second row from the first, right? And that'll give us a 0 here. So we do -2 times the second row plus the first row gives us, of course, 1, 0, 0, 1. That's why we did it. And that -2 times 3/2 is -3. It was -3, not -2. Somehow that doesn't agree. So something's wrong. Everybody see what's wrong? Oh, no. Okay, hang on a minute. Let's correct me. Okay, that didn't work, but for a simple reason that I like the individual that pointed it out. I wrote this down carelessly, then I stopped using my head. Okay. So this should be 1, 0. So when I add -3 to 1, I get the -2. Instead of a 1 here, I get -2 times -1/2, which is 1. Yeah, that's right. Okay. So now it matches. Okay. So stay more alert than I would, but this is how it's done. And you see that this will work for any size matrix. If I have a 4x4 matrix here, well, then I'm going to have a 4x4 identity matrix over here, and I'm still going to get a 4x4 matrix when I'm done reducing, right? Now, for any ordinary mortal, your chances of correctly reducing a 4x4 matrix, just a random 4x4 matrix, without making a mistake, are pretty low. Okay, but you should be able to do a 3x3. And then when you go to 4x4, a lot of times they'll ask you to do use software. And I really ought to find a way to give you a video on how to use Desmos with matrices. Okay, because there is a problem. I think there's just one on your assignment that asks you to use a computer algebra system. You can ignore that problem for now. If you learn linear algebra, it takes like 12 seconds to learn how to use software to do everything. Okay. And in my opinion, it's ridiculous to even bring the things into use at this point. But I understand the contrary argument and I kind of accept it, whether I think it's ridiculous or not. Okay. So we have that. Okay, another kind of thing that isn't like numbers. If you take the inverse of a product of two matrices, it is the product of the inverses, but in the reverse order. Okay. Now remember that AB equals BA is only true for fairly rare class of matrices. Okay. So that there's no reason necessarily you should expect this, but let's see why this is. Okay. This is easy to show. Since this times this has got to equal I, right? Well, question mark, is this times this equal I? Okay, well, by the associative law, this is the same as A times B, the inverse, times A inverse. Okay. Now, there are a couple of steps of the associative law. Well, I'm not going to worry about that. I can regroup as long as I keep things in order. I can't change the order because AB is not generally equal to BA, and if I change the order, I might get a couple of matrices in reverse order, and it's not going to work at all. Okay, so what's B times B inverse?
Should be just I.
It's identity, right? Okay. So we have A times the identity. Okay. Now, I really didn't group this in the official manner, but we're just going to wave our hands over that because we don't want to get into too many technical details, but you want to think about them when you encounter them. Okay, well, this is the same then as can group this either by grouping the A times the I or the I times the inverse, right? Either way, I'm going to get, well, if I group it this way, this gives me then A times A inverse. Is that equal to I? Yes, since these are inverses. Okay. So there's an important property of matrix alphabet. And it's going to be really important next week when we start constructing. We factor matrices using elementary matrices. And it's actually quite simple. Okay. But you don't want to confuse some of these properties, and the problems, I think, do a pretty good job of showing you what works, what doesn't, what works, what doesn't. And there's some fairly challenging problems, and there's a lot of fairly simple problems. Okay, so you got to work through. Okay. Now there's a couple other things I can talk about since I've already talked about all this. So let me make a decision here. There we go. Okay. So if we have a matrix equation, AB equals AC. Now, if these were numbers, you could conclude that B equals C, right? So if AB equals AC, then B has to equal C. Okay? It's not so. Matrices, and I'm going to say it this way, unless A reduces to the identity. In which case, then you could say, if this is the case, in that case, you can invert A. If A reduces to the identity, then the process we just saw gives you the inverse matrix, right? Okay. So if A doesn't reduce to the identity, then this doesn't work. Okay. A doesn't reduce to I, then there's a matrix which I call capital X. a little long, non-zero matrix. All right. Okay. Such that and I'm going to restate this. I should have written this out before. Make sure I got all my words in the right place. There's an invertible matrix X such that X equals 0. Okay. Well, I want to think through that before I actually lay it on you. Okay. There's a confusing step that comes up, and I'm not seeing how to get by that. So we might talk about that later, but the main thing is going to be that B equals C doesn't follow unless A is invertible. If A is invertible, it works. A is invertible, then there could be more than one. So B wouldn't have to equal C. Okay. Okay. So that's just another comment on matrix algebra. You can take that as it is. You don't need to prove it. I don't think the book proves it either. But it's fairly standard idea. A fairly standard manipulation.